It's time for another amazing chemistry video with Mr. Stapleton! Proudly sponsored by Farmer Junior Nice Coffee.
Hi guys, welcome to the next video I'm going to be doing. Today I'm going to be talking all about drawing molecules and showing how you can get the different shapes around the molecules. So I'm going to be talking about the valence shell electron pair repulsion model. Now you don't need to remember exactly what that means, okay? But basically it talks about how we use the valence shell, so the outer shell electrons of an atom, how we pair them up, and then how we use the fact that electrons which are all negatively charged will repel each other to get their shape. So the first thing you're always going to do is draw your central atom and then valence electron shells around it. Now if you don't know which one's your central atom, always look for the one that there's least of. So if you've got NO2, 2 oxygens, 1 nitrogen, it's going to be the nitrogen. If it's PCl3, you've got 3 chlorines, 1 phosphorus, it's going to be the phosphorus. So always put the one that you've got least of in the middle. If there's the same amount, doesn't matter. Then draw your surrounding atoms, evenly spacing them around the side. Okay, so if you've got 2 atoms, put one each side, 180 degrees apart. 3 atoms, put them evenly spaced around like a triangle, and I'll show you that as well. Then add your valence electrons in. When you're putting your valence electrons in, always make sure you put them individually to begin with, and then start pairing them up after the 4th one, and I'll show you that as well. If you don't know how many valence electrons an atom has, look on the periodic table. Okay, if it's in group 2, it has 2 valence electrons. Group 7, 7 valence electrons. The number of valence electrons always equals the group number. You can never go wrong. Then connect your lone valence electrons first, alternating by 90 degrees each time, and then redraw it, getting rid of all valence electrons except for those around the central atom that are important, right, because they determine a couple of the shapes. And if it's got a charge, you need to put your brackets in and show the charge as well, so I'll show you that. So let's get started with just a really simple one. Okay, I'm going to take a hydrogen and chlorine. So we're actually going to do hydrochloric acid. Okay, now I've drawn it like that because that's actually the shape for the moment, but I'll show you how we get to that. So because there's an even number of them, it doesn't matter which one we start with. So I'm just going to start with the hydrogen. Hydrogen's in group 1, so it's got 1 valence electron around it. So generally we show valence electrons with a little dot like that. Okay, I go to chlorine. Now, some people like to do different things for each atom, so sometimes you'll see some people put some X's on the second one. I just like to keep it simple, okay, and draw the dot around it. Okay, so we've got our dot, okay, there for chlorine. Now chlorine's in group 7, so there's our first electron, okay, that's group 7, okay, so that's going to have 7 valence electrons. That one's group 1, so that's going to have 1 valence electron. So to start off with the chlorine, we put 1 there, then we put a second one in, then we put a third one in, then we put a 4th one in. Alright, so what we're actually doing is we're putting them at 90 degrees. Now we start doubling them up. So we get another one, that's 5, 6, 7. Okay, and actually put that on the side so it looks a bit nicer. Okay, so there's our 7 valence electrons around the chlorine, there's our 1 valence electron on the hydrogen. Okay, so this one's really straightforward. We now go to actually start to joining up the lone valence electrons. Okay, so we've got 1 here, we've got 1 here. So we join them up together, that creates a bond. Every bond is 2 valence electrons. As you can see here, what we've got is now a full outer shell on the chlorine. We've got 1, 2, 3, 4, 5, 6, 7, 8 electrons there. That gives it a full outer shell. The hydrogen has 2 electrons in its outer shell. Okay, because it only has a 1s orbital, all it can hold is 2 electrons, so that actually makes it full as well. So what we would redo is we would redraw that as HCl, and because all of our atoms in a line, this is a linear shape. Okay, so that one's a really straightforward one. A linear molecule, but this time it's got 2 atoms either side, so I'm going to go with carbon dioxide, CO2. I'm going to put our central carbon atom in. Carbon's in group 4, so it's got 4 electrons around it. So 1, 2, 3, 4, evenly spaced, 90 degrees apart. We're going to put our oxygens on either side because there's 2 of them. It's going to evenly space them. Now oxygen's in group 6, which means 6 valence electrons. So 1, 2, 3, 4, 5, 6 for that oxygen. And I'm going to go the reverse on the other side, and hopefully you'll see why in a minute. 1, 2, 3, 4, 5, 6. Now what that actually does is that nicely puts the paired electrons on either side. What we now do is we join up the valence electrons. Now remember, every atom wants to get a full outer shell. carbon and oxygen are both in period 2, so the most they can have in their outer shell is 8 electrons. So we start bonding up, okay? Bonding up this one, okay? Then bonding up this one, okay? Then we can bond up that one and bond up that one, okay? It doesn't matter basically what way you do it and if you have some crossing over, and I've done that deliberately this time to show you, okay? Because all that matters is the final arrangement we get around it. The carbon atom in the middle has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. The oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8, and this one also has 8 around it as well. So they've both got a full outer shell. So we draw the carbon again in the middle. This carbon has 1, 2 bonds going across to an oxygen, has 1, 2 bonds going across to an oxygen that way. They're evenly spaced because there's no lone pairs of electrons around the central carbon, which gives us a linear shape for carbon dioxide. So let's have a look at some where we add in a couple more. Okay, and what I'm going to look at is phosphorus trichloride. So that's PCl3. Okay, so with phosphorus, phosphorus is in group 5. That's the one we've got least of. So that's our central atom. So we draw our phosphorus in the middle. We put our central atom with our valence electrons. So this has got 5. Just putting them around like that. Now we've got 3 chlorines. So I want to evenly space them this time. So we're going to put 1, 2, 3, just as evenly as I can. Doesn't matter basically the arrangement of where they're, if they're over here or here, doesn't matter, as long as they're evenly spread. Chlorine has 7, and I'm just going to start to go through these quickly now. So it's got 7 electrons. Notice what I'm doing is I'm putting the lone pair of electron closest to the central atom. If you can, it makes doing your bonds a lot easier. Okay. Now start pairing up your lone pairs of electrons. So we've got 1 there, 1 there, and 1 there. Okay. Now, what you'll notice on our central atom is a little bit different to what we've had before, is we've actually got a lone pair of electrons. These lone pairs of electrons, what we've got over here is a bonding region, which is negatively charged, because it's got 2 electrons. We've got a bonding region here, which is negatively charged. Okay. What's going to happen is that this negative charge here from these electrons is actually going to repel these bonding pairs of electrons downwards. Okay? And what you've got to remember is that even though we're drawing this in 2 dimensions, these are actually 3-dimensional molecules. So what we end up with is a phosphorus in the middle, okay? And because this lone pair of electrons up the top is repelling these bonding pairs of electrons downwards, we end up with these chlorine atoms actually bent downwards, okay? And in 3 dimensions, this one's actually coming out, and this one's going in, so we've got a 3-dimensional structure there. Because down the bottom here, we end up with what looks like a bit of a pyramid, okay, if you actually join those up, okay, because we've got 3, that means it's trigonal, and we form a pyramid, so it becomes a trigonal pyramid shape, okay. You would not draw in these blue lines though, you would leave carbon tetrachloride as that shape with the lone pair of electrons, okay. Let's go on to another one. If we add more in now, let's look at carbon tetrachloride, CCl4. Take our central carbon atom, 4 electrons, 1, 2, 3, 4. And what I'm going to do is put 4 chlorine atoms around it, evenly spaced. So we've got chlorine, 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 chlorine there. Add in our valence electrons. Remember, I'm keeping my lone electron closest to the central atom. Like this. And I'm sure you're probably already seeing how we're going to bond this up. Okay? Just joining your 4 together, like that. We get a full outer shell around our chlorines and around our carbons. Okay? Everyone's happy. So we redraw this molecule like this. However, you've got to remember these are 3-dimensional shapes. So what we try to show is that we've actually got a 3-dimensional structure. Like the trigonal pyramid, we end up with 1 chlorine, this one coming out of the page. Don't know why I've done a hydrogen there, sorry. Okay, and 1 chlorine here going into the page, and we end up with those 4 central atoms. Obviously, the word for 4 is tetra, so it is a tetrahedral shape. Okay. Now, those are pretty straightforward. I'm going to show you a couple more and show you another one that involves a lone pair of valence electrons. So let's show a really common one that lots of people draw. Alright, water, H2O. Central atom this time is going to be our oxygen in the middle there, O. Got 6 valence electrons around our oxygen. Okay, and again, I'm just doing that quickly, but you could go 1, 2, 3, 4, 5, 6 when you're drawing. Draw your hydrogens on either side. Okay, 1 valence electron for each of the hydrogens. Okay, you bond up the hydrogens like that. Okay, now what you'll notice here is you've got 2 lone pairs of electrons. And remember again, this is a bonding section of negative charge. This is another bonding section of negative charge. We've got negative charge over here, alright, a negative charge there. So these are going to repel these bonding regions. That's going to repel the bonding regions, and these are going to repel each other as well. So what we actually end up with is a shape that looks like this. Oxygen in the middle, hydrogen that's being repelled downward because the lone pair of electrons is repelling the bonding pair of electrons, or the bonding region I should say. So that's that lone pair of electrons doing that. And that's repelling away this other one here. So if you actually have a look, if we drew lines in here, you can see they're all kind of 90 degrees away from each other, getting maximum separation. And that is what we call a V shape. Okay? Hopefully that makes sense because it's an upside down V. Okay? But it's always those lone pairs of electrons. Remember to put those in on the central atoms. Very important because they actually determine the structure. You need to put both in. Alright. So remember what I said about how each atom likes to get a full outer shell, and so far we've been looking at that as 8 electrons. What do you do though when you start to get to something a little bit more complex, like the sulfate ion, SO4? And it's actually got a 2- charge. So I'll show you a couple of things in this one. One's called the expanded octet, which is for anything in period 3 onwards, which can go beyond 8 electrons in its outer shell. And also I'm going to show you how we have a charge and where that charge comes from. So again, we've got our central sulfur atom here. Sulfur's in group 6, so it has 6 electrons around it, just like that. Okay, we've got 4 oxygens, and I'm going to just move that so I can show you a little bit more easily. So we've got 1, 2, 3, 4, 5, 6 there. Right, another oxygen over here. 1, 2, 3, 4, 5, 6. Another oxygen here, spacing them evenly around. And another oxygen over here, spacing them evenly as well. Okay. Now we start bonding up our lone pairs of electrons first. So let's do that one. Let's do that one. All of a sudden we're out of lone pairs of electrons. But if you have a look, sulfur's got 1, 2, 3, 4, 5, 6, 7, 8 electrons already. So how do we bring these other 2 oxygens in? Well, that's where the expanded octet comes in. Sulfur goes beyond its normal 8 electrons. All right. So that's where the 3d orbitals come in. Okay. So let me actually show you here. So we're actually going to bond up these ones so that that oxygen's got a full outer shell. We're going to bond up this one so that that oxygen's got a full outer shell. Now what you'll notice is that these 2 oxygens still have a lone electron each. What's the charge on an electron? -1. If there's 2 lone electrons there, we're going to get a 2 negative charge. That's where it comes from. So to redraw this, you have a sulfur, you have a double bonded oxygen atom there, you have a double bonded oxygen atom there. Okay, that's the ones, those ones. It doesn't matter if you put it over on the other side, we just tend to put identical things opposite each other. Okay, we have a single bonded oxygen over there, a single bonded oxygen over there. We don't need to show the lone pairs of electrons on the oxygen because they don't determine the shape. You don't need to show the lone pairs of electrons on the oxygen either. Sorry, the lone electrons on there. Because what we do is we put a big bracket, a square bracket either side, and we put a 2- charge in there. That shows us, right, that we've got 2 lone electrons. All right, really straightforward. If we wanted to turn this into sulfuric acid, okay, so instead of the SO4 2-, if we have H2SO4, we just bring in our hydrogens. So there's one there, okay. They would now bond up to these lone electrons, and we would get a shape that looks like this. Okay. Oh, now you can draw in the hydrogens like that, a V shape around the oxygen, or you can do that. All right. Make sure you have the oxygen as the one with the bond, okay? Because that's what bonds to the sulfur, and that is a tetrahedral arrangement. Because what we're looking at is around the central atom. There's 4 evenly spaced. That's tetrahedral. Okay. So I'm going to show you one more, because this is now introducing something called a coordinate covalent bond. This is the final special type you can have. So I'm actually going to show you the nitrate ion, NO3-. So our nitrogen is in the middle. That has 5 valence electrons, like that. We've got 3 oxygens, so we evenly spread them around, like that. Each of them's got 6. Once you guys are quite comfortable with this, you can probably go a bit quicker. You may not feel the need to have to draw these valence electrons in, but it's always a good little practice to do it if you want to. So what we do, we start bonding up these lone electrons. Okay, so if you did it normally, you'd kind of go, alright, like that, like that, like that. No lone electrons left. Okay. No lone electrons left. But however, nitrogen's only in period 2. So what that means is it can't expand its octet. So already it's got 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. We can't do anything more. Plus, if we've got 1, 2, 3 lone electrons there, that doesn't give us a 1- charge. That would give us a 3- charge. So that can't be right. So what we're going to have to do is start again. Okay? Let's look at bonding up one of these oxygens so it's got a full outer shell. So let's do this one here. Okay? So that gets that oxygen done. Alright? What can we do now? We've got one lone electron over here. So if we pair that up, we've got 1 electron here. Now, the problem is that this oxygen over here needs 2 more electrons. What happens is that both of these electrons here, they actually form a bond over here to the oxygen. So this is a sharing of valence electrons here, okay, where one atom shares both of them, and that's called a coordinate covalent bond. That's where one atom donates both electrons to it. So if you actually have a look, we haven't broken the octet rule for nitrogen. The oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So everything's got a full octet. Right? All we've got left is this one lone electron on the oxygen over here, which gives us our negative charge. Okay? So we can redraw this, the nitrogen. Okay? We've got this double bonded oxygen here. Alright, so I'm going to show it that way this time. Okay? We've got a bond over here to the oxygen. Okay? We've got a bond over here to the oxygen as well. Now, what used to happen is we used to show this with a little arrow as a coordinate covalent bond. Okay? We don't actually have to do that anymore. So you can just leave it as a single bond. Okay? It's implied that it's a coordinate covalent bond. You put brackets around it and you put the negative sign in. That is a 1, 2, 3 around the middle. Alright? It doesn't form a pyramid anymore. They're all in the same plane. So if you imagine this is one plane, so one dimension. Okay? So that makes it a trigonal planar molecule. Alright? That's all I've got time for. I'm just showing you some of those main structures. If you follow those rules I've shown you of drawing your central atom, putting the valence electrons in, spacing your other atoms around evenly, putting those valence electrons in, starting to bond them up, alright, you'll be able to very, very easily hopefully draw your molecules. Remember, the main shapes are linear, alright, so learn these. V shape, trigonal pyramid, that has a lone pair of electrons, alright, trigonal planar, and tetrahedral. Get used to these, find as many as you can, download the worksheets on drawing the structures, have a go, Any more questions, ask me. Thanks guys, good luck.